All right, hi everybody. Welcome to Lecture 6.1, covering the topics of convection and buoyancy. We're going to talk today about how buoyancy and convection are connected, and about how buoyancy and the force of buoyancy is fundamental to understanding convective transport in stars. So as we've discussed already, there are three primary mechanisms for heat transport in stars: radiation, conduction, and convection. Radiation, we spent a lot of time talking about. This is one of the primary mechanisms for heat transport in stars. This is photons diffusing out from the center, carrying heat and energy to the surface, and eventually escaping into space. Conduction, we've talked a little bit about. This is literally thermal conduction between interacting electrons colliding together, sharing energy, transporting their heat via a diffusive process. Typically speaking, this is a subdominant effect for heat transport in stars. Most stars simply aren't dense enough for conductive heat transport from electrons to be very efficient. It just doesn't move enough heat compared to radiation diffusion and convection, our last form of heat transport in stars. And this really has to do with large-scale motion, moving some hot fluid to a colder place where that hot fluid gives up its energy, warming up that colder fluid. This is, along with radiation diffusion, one of the two most important mechanisms for heat transport in stars. And in order to correctly model stars, we must include convection, both the heat transport from convection and also the mixing that is induced by convection. So we're going to start talking about that now. And all of this is really underlined by Archimedes' law, which says that the buoyant force on an object, either wholly or partially immersed in a fluid under a constant gravitational acceleration, equals the weight of the fluid it displaces. Right? And so this is something somewhat familiar to us, right? We know that if we stick a boat in water, it'll float, right? Why does it float? Not because the boat is made of material that is less dense than water. We know that we can make boats out of steel and they still float. The important point is that the boat, the object, whatever, displaces a greater mass of water than it itself weighs. And so we can start to understand this a little bit from a theoretical point of view with Archimedes' law in the following way. So if I were to take my little boats here, and so we've got a couple of images here from figure 6.2 in the notes. The first is a boat with a weight sitting in it, and the second, we've dropped that weight to the bottom. But to understand the buoyant force and how displacement works, let's make a few definitions. One, we're going to say that the density of water is going to be rho W. Cool, fine. And we're going to say that our boat has mass m. So our little boat has a mass of m. And when it is in the water, the volume of water displaced by the boat, pushed aside by the boat, we're going to call that V, big V. All right. So then, now, we know the force on our boat, right? The force acting on my little boat in the water. If I were to put my little boat here in the water, looks like that. Maybe it's a sailboat. I don't know. But there is a force acting on this boat, which is mg, where g is the constant gravitational acceleration, pulling that boat down. Right? The force up, if the boat is static, if it's not sinking, if it's not flying out of the water, if it's static, it's just floating in a stable configuration, then the buoyant force pushing back up must equal this. Right? And that buoyant force is equal to the weight of the water that is being displaced by the boat. Right? So we know what that is. So the weight of displaced water will be the density of water times the volume displaced, that's a mass, times the gravitational acceleration. This has got to equal that, mg. And so if we set these two things equal to each other, times g is equal to mg. What we find out, what we get out of that, very simply, is that the displaced volume has got to be equal to the mass of our boat divided by the density of water. Easy peasy. So, let's consider an example, and this is exercise 6.1 in your book, which says, suppose we have a toy boat, like in our image here, carrying a weight and floating in a tank, as shown in the top panel of figure 6.2. The depth of the water in the tank is d. So the depth from the bottom of the tank to the top of the water line is d. The weight in the boat is then removed and dropped to the bottom of the water. It sinks to the bottom of the tank, bottom panel. Does the depth of the water in the tank increase, decrease, or stay the same? Explain your answer. So now, let's take this guy here and consider this problem. So here's our little boat guy. We're going to move him down here. So we've got this boat again. Here's the same image once more. All right. So now we need to consider all of the forces acting on this boat in the two scenarios to figure out what is actually going on. All right. So we know that initially, in this case here, move that there. So in this case here, if the boat has some mass in it, and it's got some mass, we know from the equation that we've got above that the volume displaced by the boat will be equal to the mass of the boat plus the mass of the weight, all divided by the density of water. All right? That's what we know. In the second scenario, the volume displaced, we'll call that d, volume displaced, is just simply the mass of the boat divided by the mass of water, but wait, the weight is also displacing some water. It has some volume, right? That it is displacing. And that, again, that weight displaced by our little weight, which has dropped to the bottom, is equal to the mass of the weight divided by the density of water. So the total amount of volume displaced is the sum of these two, right? Which leads to the total volume displaced is then the sum of those two things, which is the same. Mass of the boat plus mass of the weight divided by the density of water. Now, that's the scenario where you were to drop the weight into the tank itself. And so since the volume didn't change, right, the volume displaced didn't change, the height of the water, d, is not going to change. But if we were to take that weight and drop it out of the tank instead, in that scenario, we wouldn't have this, and we would then have a less volume displaced, and the height of the water would decrease, right? The height of that water would decrease in that scenario. But in the case where we drop the weight in the tank, it stays the same, right? The same amount of volume is being displaced. So that is an example of using Archimedes' principle to calculate what the buoyant force might be. And that buoyant force is going to be equal to the amount of water mass being displaced times the gravitational acceleration. That's pretty much